We are going to begin talking about Unit 2. This video is going to focus on learning target 2A, which is what is a derivative. So there are three ways that we can think about derivatives: graphically, algebraically, or theoretically. Graphically, the derivative at a point is the slope of the tangent line at that point. Algebraically, the derivative is the limit of a difference quotient, and theoretically, the derivative represents the instantaneous rate of change. Now, all three of these are helpful depending on what type of problem and what kind of scenario we are given. We're going to start with the graphical approach and talk about what a tangent line is. So a tangent line to a point on a curve is a straight line that only touches the curve at a single point and grazes the curve at that point. So down below here we have two graphs. The graph on the left is not a tangent line, it's a secant line, but the graph on the right is what a tangent line looks at. So we can see here how on this graph, this red tangent line is grazing or touching this curve at exactly one point, which is a comma f of a. But how do we figure out how to get a tangent line? Well, we have to start with a secant line like we have on the left. So on the left, in black, I have my f of x curve here, which is my function, and I have 2 points on those curves, and I can draw a straight line through any 2 points, and that would create a secant line. So it's going through the point P down here at a comma f of a, and also this point Q, which is at x comma f of x. Now when I have a line, I would calculate the slope of it. So I could find the rise over the run. The rise here would be our delta y, which is this f of x minus f of a value, or our change in y values. Over the run is this delta x, which is our x minus our a, so our change in those x values. We could find the slope of that secant line by using our rise over our run and getting delta y over delta x, or f of x minus f of a over x minus a. And that's going to come up later on when we actually talk about this algebraic approach to a derivative with the limit of a difference quotient. Now, how do we get a secant line to a tangent line? So what we would do is we would move point Q down f of x so it gets closer and closer to point P. In doing so, I could create a bunch of tangent lines on here. So if I move point Q down to this point, I would have another secant line that would run through those 2 points, and I could do this an infinite amount of times until I end up with point Q on top of point P. What happens here with this that is important to notice is that the distance between our x and our a value is getting smaller and smaller. So as point Q moves down towards point P and we get other secant lines, what's happening is the distance between x and a gets smaller and smaller, which means that this delta x value here is approaching 0 since they end up at the exact same point at a. In turn, what happens is that we end up with a tangent line that grazes f of x at this single point P. So you might be wondering, okay, well now I have a tangent line, how does that connect back to this limit of a difference quotient? Well, the difference quotient, by definition, is our slope. It's the change in y over the change in x, or that f of x minus f of a over x minus a that we had up above here from our secant line. Alternatively, we could rename a lot of these values. Instead of using a, I could have an x value and then x plus h, where I've moved over so many units h, and in turn, when that happens, we get this form of the difference quotient, which says f of x plus h minus f of x over h. So this is coming from our standard slope formula, where I have 2 points, x and x plus h, and I've replaced those in there. So I've replaced x with this x plus h, and then we've replaced a with this x value. And so that change, that delta x there, is just equal to this h, since that's the difference between x plus h and that x distance. These two forms here of the difference quotient are used most often in a calculus course. We've seen this f of x plus h minus f of x over h difference quotient, and then we also have this standard slope of f of x minus f of a over x minus a. Our third way to think about a derivative is theoretically with the instantaneous rate of change, and that is the rate of change of one quantity compared to another at a particular instance or a point. Later on in this course, we are going to look at motion problems, and we're going to deal with velocity and acceleration, and we're really going to talk about the theoretical side of the instantaneous rate of change when we look at some more application type problems. Okay, let's look at the formal definition of a derivative. That distance quotient is going to pop up with our definition here. Since our derivative, remember, is the slope of the tangent line, and we got the tangent line from that secant line slope getting smaller or approaching together. So the formal definition of the derivative of f of x is the limit of the difference quotient. So we have two notations for the derivative. This operator notation of dy over dx, and then this prime notation, which would be represented as f prime of x. Now, both of these represent the derivative of our function, and by definition, the derivative is the limit of the difference quotient. So we have here the limit as h approaches 0 of f of x plus h minus f of x all over h, assuming, of course, the limit exists. As we're going to talk about later in this unit, not every derivative does exist, but for now we are going to assume that any function we're trying to find the derivative of, that derivative does exist, and later on at the end of this unit we'll talk about, well, what happens if that's not the case. Now in this limit, it's important to notice what our h value is approaching. The reason h is approaching 0 is that h is this distance in between our 2 points. And as we move from our secant to our tangent line, that distance was getting smaller and smaller and was approaching 0, which is why in the limit we have that h approaches 0. When this limit exists, we say that f of x is a differentiable function, meaning that the derivative exists. Now, alternatively, we could look at what happens when we had this slope type of difference quotient instead. So this first definition here on the bottom of page 43 for you guys is the derivative of f of x in general. On our next page, we're going to look at what happens if I want to find the derivative at a specific value x equals a. Now we can apply that same definition at a single point, and let's just call that point x equals a like we had up in the picture above. Now when we do that, we're evaluating f at x equals a, and we have to take that into account. So up here, when we had our general derivative, I had my f prime of x or my dy over dx. Now that we're evaluating that into a, you'll notice I no longer have f prime of x, I have f prime of a instead, since I'm substituting in a in place of x. For the operator notation, we have this vertical bar here. So we still have this dy over dx, then we have that vertical bar. How we pronounce that is that's referring to evaluated. So this is saying dy over dx, which is our derivative of y with respect to x, evaluated at, in this case, x equals a. So that vertical bar is telling us what x value we want to substitute in. Now we have our same limit here. We have the limit as h approaches 0 of now, instead of having x's in our difference quotients, we have a's. So f of a plus h minus f of a over h. Alternatively, we can use that kind of slope form of our difference quotient, and I could find, again, f prime of a or dy over dx evaluated at x equals a. Using the slope form of our difference quotient, we would get the limit as x approaches a of f of x minus f of a over x minus a. Remember, this is our change in y over change in x that we're used to seeing from an algebra course. And again, if this limit exists, we say that f of x is differentiable at x equals a, meaning the derivative of f does exist at x equals a. So far, just looking at the formal definition of a derivative, we can see that we have two notations going on. Not only do we have this operator notation of that dy over dx, but we also have this prime notation with f prime. Then we also have the difference between a general derivative, which was up above here, so a derivative at any value of x, versus a specific derivative down here if I'm substituting in a specific value for x. Now, they are still the same definition, it just depends on if we're trying to find a general derivative or a specific derivative at a point. Now for notation, we do have some more notation that can come into play. depending mainly on if I'm using y equals or f of x equals. So on the left-hand column here, we have all the prime notations and how we would pronounce those. Then on the right, we have all of our operator notations. So if I have a function y equals f of x, and I have some constant a, for the prime notation, there's a couple ways we could write this. F prime of x would be read as literally f prime of x, and that represents a general derivative of f at any point x. Then we have this f prime of a, which is a specific derivative when x equals a. Oops. So we have our general on top and then our specific down below. If instead I want to use y instead of f of x, I could also use y prime, and that would be a general derivative as well. Now for our operator notation over here on the right, similar things. So this d over dx is representing a derivative. That's telling me that I want to take the derivative of whatever my input is here. But because that's a little cumbersome to write, we can kind of combine it all into one with this dy over dx. And the way we pronounce that is that's read as the derivative of y with respect to x. So this WRT is shorthand for with respect to. So dy over dx is read as the derivative of y with respect to x. So you might be wondering, well, does it matter what I'm taking the derivative with respect to? And it absolutely does. Later on in this course, we're going to talk about maybe instead of having x and y as my variables, maybe I have time and I have f of t instead. And we're going to want to keep track of what we're taking the derivative with respect to. Especially when we start talking about some applications later on, we can definitely switch up the variables, so we want to make it clear which derivative I'm taking and what I'm taking it with respect to. Now we could do this as a derivative at a point as well. So the second line here is our specific point at x equals a, and this would be pronounced as the derivative of y with respect to x at x equals a, or again, we could use that evaluated at phrasing instead, or you could just say at x equals a. And then the last notation here would be if I want to use f of x in place of y, I could take the derivative of f with respect to x as well. All these notations mean the same thing. So f prime of x equals y prime equals the derivative of y with respect to x equals the derivative of f with respect to x. All of these notations are interchangeable, and you will see them used throughout the course on a learning check, on your practice, within the ed puzzles, and then also on the AP test as well. One important thing I do want to point out to you guys is that d over dx by itself should not be thought of as a fraction or as a derivative. It should be thought of as an operator that instructs you to take the derivative and treat x as a variable. So just having a d over dx by itself without any input doesn't make sense. Just like we've talked about before, having a square root without an input, that doesn't make any sense, or having a limit as let's say x approaches 2, but without having an input, all of these notations don't make any sense because I don't know what I'm trying to take it of. And so this operator notation of d over dx only makes sense if I have a function that I'm taking the derivative of, which is why we have that derivative of y with respect to x properly written. Let's do some examples using the definition of the derivative. So, for our first example, it says use the definition of the derivative to differentiate, which means take the derivative of this function, which is y equals x squared minus 4x plus 15. So I'm going to write our general derivative up above, which says the limit as h approaches 0 of f of x plus h minus f of x all over h. And this represents our f prime at x. So I'm using the general derivative here because they didn't give me a value for x, they just said to differentiate that function. So to use this, let's set it up. I could also call this y prime since I do have that function y equals instead of f of x, but as we know from prior courses, y and f of x are interchangeable. So let's start this. We're trying to find the derivative, so I'm going to start by writing y prime since that's what we're actually computing. That, of course, is equal to our f prime of x, and I'm going to start setting up this limit. So we have the limit as h approaches 0. Now to find f of x plus h, what that means is I want to substitute in an x plus h every place I have an x here. So I have an x squared, then I have a negative 4 times x. So each one of these x's I'm going to replace with an x plus h, since that's what the composition here of those two functions means. So if I just write out the f of x plus h part, I'd get x plus h, the entire thing squared, since that's getting substituted in for that x, minus 4 times, make sure I have parentheses around this, the whole x plus h plus 15. So that portion right there that I have written is just this f of x plus h. Now I have to subtract off the entire original function, which is f of x. And again, y and f of x are interchangeable. Now I'm going to sub in this quadratic exactly as it is, but I do want to make sure I have parentheses around it because that negative sign would need to get distributed to all the terms here. So I'm going to have minus, in parentheses, the x squared minus 4x plus 15. Now, all of that right there is all over h. So that's our setup. Now from here, we're going to play a simplification game. I'm going to want to kind of multiply out and combine like terms as much as I possibly can. I can't take the limit yet, because right off the bat, if I were to sub in 0 for h, I'd be dividing by 0, which is going to give us an issue. And on top, if I substitute in 0, I'd actually also get 0. So I have an indeterminate form there of 0 over 0, which means I need to do some type of algebraic manipulation to be able to solve this limit. The algebraic manipulation I'm going to do is honestly to multiply everything out and see what like terms I can combine. So to FOIL the x plus h squared out, remember, it's a little side note here, x plus h squared is the same thing as x plus h times x plus h. I don't just square each term, I have to FOIL that whole term out. FOILing that out, I'd get an x squared plus 2xh plus h squared. Distributing the negative 4, I'd get minus 4x minus 4h plus 15, and then distributing the negative sign, I'll get negative x squared plus 4x minus 15. All over that h still. Now from here, I want to see if I can cancel any like terms. So the x squared and the negative x squared will cancel. The 2xh will not cancel, neither will the h squared, but that negative 4x and the positive 4x will cancel, then the plus 15 and the negative 15 will cancel. So what we're left with then is the limit as h approaches 0 of 2xh plus h squared minus 4h all over h. Now I cannot combine any like terms from here, but I still need to be able to algebraically manipulate this, because if I do a direct sub again and I sub in 0 for h, I end up with 0 over 0. Now one of our ways to algebraically manipulate was to factor. And on top, each one of these terms has an h in common, so I'm going to factor out an h. What that will leave me with is a 2x plus h minus 4, oops, that was a minus, all over h. What we can do from here is I can cancel an h over an h, and that will give me a value of 1. And I'm now just looking at the limit as h approaches 0 of 2x plus h minus 4. Now we can finally do a direct substitution, and when I substitute in 0 for h and I simplify, I end up with 2x minus 4. What that is representing is this is the derivative of our function y. So we were able to find the derivative by using the definition, which is the limit of the difference quotient. Now this is definitely a long and tedious route to get to the derivative, and some of you might already know about our shortcuts to get to our derivatives, but we're not going to talk about those until our next section. The key I want to remind you guys with taking the limit of a difference quotient is to really be careful in writing out all of your steps. It's really easy to make an algebraic error up here as we're foiling and combining like terms, and one tiny little algebraic error can actually throw off your entire answer. So we want to make sure we just take the time to write everything out. And then, as always, don't forget that if I'm squaring something, it's the same thing as itself times itself, and I would FOIL that whole term out. Let's look at example 2. So example 2 says using the alternative definition of the derivative. So that alternative definition, if you flip back in your course reader, that alternative definition is the limit as x approaches a of f of x minus f of a over x minus a. And so they're telling us to use that alternative definition. This is representing f prime at a, since that's specifically representing the derivative at that value a. We're going to use this to differentiate this function, f of x, which equals 4x minus 5, at just x equals a in general. So it might seem silly that I'm replacing a variable with another letter, but this is still representing that same value. So I'm just going to substitute in a instead. Okay, let's set this up. So we're going to find f prime of a. So I will have the limit as x approaches a. My first thing I need is f of x, which we have. That's that 4x minus 5. Minus, I need an f of a, so I'll substitute in an a in place of all the x's. So I'll get 4a minus 5 all over that x minus a. So take a second to make sure that you agree with the setup there of the f of x minus f of a over x minus a. From here, let's simplify what we can. Why don't you guys pause the video and combine any like terms that you can. What we can do to simplify this is if I try to do a direct substitution, I will end up with 0 over 0. So I'm going to algebraically manipulate by distributing that negative sign. So we get 4x minus 5 minus 4a plus 5, since I have to distribute that double negative there, over x minus a. From here, the only thing that's going to cancel is the 5's, but that's okay. Let's see what happens. We're left with then the limit as x approaches a of 4x minus 4a over x minus a. From here, our goal is to ultimately direct sub in if I can, but again, I'm still left with 0 over 0. So the last thing I can do is factor out a 4, since both the 4x and the 4a have a 4 in common. What that leaves me with then is 4 times x minus a over x minus a. So the x minus a's will cancel, and we get left with the limit as x approaches a of 4. Now I'm just taking the limit of a constant, so that will leave me just with that constant. And what that 4 is representing, let me see if I have enough space underneath, I do, that is representing the derivative of f of x at x equals a value. So through these two examples, we can see how we're using the definition of the derivative to compute that derivative out the long way. Now we are not going to do a ton of these problems. We are going to move on to the power rule, product rule, quotient rule, and chain rule when we are working with our derivatives in the next section, but it's important to understand where all of those come from and that a derivative is the limit of a difference quotient. So all that stuff about limits that we learned in our last unit is helping us build all of these concepts about derivatives. Now the last part of this video is going to just be setting up a bunch of problems. So in problems 3 through 6, what we're going to do is set up but not solve the definition of the derivative for these different functions f of x at some values for x using both the regular and the alternative, just so that we're used to recognize these and setting them up. So in purple here, I'm going to write out the regular definition that we're used to. So our regular definition is f prime of a equals the limit as h approaches 0 of f of a plus h now minus f of a all over h. And then in blue, I'm going to write out our alternative definition, which is also representing f prime of a. But that will be the limit as x approaches a of f of x minus f of a all over x minus a. And that stuff was from our last example. So what we're going to do is set up both the regular and the alternative for each one of these examples, but we are not going to solve them out from there. So for our first example, in example 3, f of x is equal to x squared plus 3, and we're evaluating this definition at x equals a. So on the left-hand side here, let's set up the regular definition. Why don't you guys pause the video and practice setting up that regular definition on your own first, and then we'll check it together. So as we go to check this, this will be the limit as h approaches 0. I need f of a plus h, so that means everywhere that I have an x, I'm going to sub in an a plus h. So I'll get a plus h squared plus 3, minus our f of a, so that means I'll sub in an a in place of all those x's. Again, I want to make sure I'm putting it in parentheses since the whole thing would be have the negative sign distributed to it, all over h. So there's our setup for the regular definition. Now why don't you guys pause the video and do the setup for the alternative definition. So for our alternative definition, we have the limit as x approaches a of f of x, which is just that x squared plus 3 that was given, minus f of a, which will be our a squared plus 3, since we substituted an a for x, all over x minus a. And for both of these, we could combine like terms and actually solve it out, but we just want to practice setting these up. Okay, let's look at example 4. In example 4, it says set up but do not solve the definition of the derivative for f of x, which is 1 over x plus 3, at x equals 1 now. So up above in example 3, you'll notice I wrote f prime of a for both of these because that was the value that I was substituting in and finding the derivative at for x. But now I'm going to be finding f prime of 1 since that's our a value. Why don't you guys pause the video and do the setup for the regular definition for example 4. So as we go to check this, we have the limit as h approaches 0 of f of a plus h. So our a value is 1. So I'm going to do this in kind of 2 lines up here and find f of a plus h, which for this example will be f of 1 plus h on its own first. That will be 1 over 1 plus h plus 3. So in that first part of our limit, I'll have 1 over 1 plus h plus 3, which of course you can simplify that down to be 1 over h plus 4 if you want to, minus I'm going to need my f of a, which would be our f of 1, and that will come by substituting 1 in for x and getting 1 over 1 plus 3 all over that h value. And again, you can simplify and combine those like terms in each of those fractions just to make it look a little bit nicer. Let's look at our alternative definition. Again, we're finding f prime of 1 since that's our a value. Why don't you guys pause the video and find that limit set up on your own first. So checking your limit here, we're going to have the limit as x approaches 1, since 1 is our a value, of f of x, so that 1 over x plus 3, minus our f of a, which is that f of 1 again, so 1 over 1 plus 3, all over x minus a, and then our a value, of course, is 1 for this guy. So I left those both very unsimplified, but I think it's helpful to see where all of the moving pieces are coming from. Okay, let's look at example 5. I want to leave the regular and the alternative up above, so why don't you guys pause the video and find both the regular and the alternative definition for y equals the square root of x plus 3 at x equals 0. Okay, let's check example 5. So for both of these, since our a value is 0, we're trying to find f prime of 0, or that derivative at 0. My first one will be the limit as h approaches 0 of f of a plus h. So for this one, that will be 0 plus h, which would just be the same thing as f of h. So we'd get 0 plus h plus 3. So we'll end up with the square root here of 0 plus h plus 3 minus f of a, which would just be f of 0 for us, which will be the square root of 0 plus 3, or just the square root of 3, all over that h value. So there's the regular definition. The alternative definition, we're also finding f prime of 0, but for this time we're looking at the limit as x approaches 0, since our a value is 0. So both of these look very similar since our limit's approaching 0, but the setup will be a little bit different. We have that f of x, so that square root of x plus 3, minus the f of a, which is our f of 0, so the square root of 0 plus 3, all over x minus 0. And I know that can be simplified down a lot more, but I really want us to see where each of these pieces is coming from. So we have one more example in this section. So in example 6, it says set up but do not solve the definition of the derivative for f of x equaling cosine of x at x equals pi. So here our a value is going to be pi, and it says using both the regular and the alternative. Why don't you guys pause the video and set up both of these limits on your own first. Okay, let's check these. So for both of these, we're finding f prime of pi. So we're going to have the limit here as h approaches 0 of f of a plus h. So let's find that off to the side. So this time that would be pi plus h. So that would be equal to cosine of pi plus h. So I'll have my cosine of pi plus h minus our f of a, so in that case that would be our f of pi, so that would be cosine of pi. And now this I do want to simplify because we want to get used to simplifying our trig functions, and it's a good review. So cosine of pi is equal to -1, so I'll get minus that -1, or you could write +1, all over h. So there's our regular definition. The alternative one will be f prime of pi, which is equal to the limit as x approaches pi, since pi again is our a value, of f of x. So that's cosine of x minus f of pi, which would be that cosine of cosine of pi, which is equal to -1. So I'm substituting in the -1 all over x minus pi. Again, all 4 of these can be simplified down more by combining some like terms, but I want us to just get some practice with the setup. And I know I said earlier that although we won't be doing a bunch of definition of derivative problems, the reason I bring these up is that this is another way to take limits. And sometimes on a learning check, you might get a limit that's really representing the derivative of a function. And after we learn all of our shortcut rules, an easier way to take some of these limits would, instead of trying to algebraically manipulate them and combine like terms and go through that whole algebraic mess, if instead we recognize that that's a limit that represents the derivative of a function, we can instead find the derivative of that function and then substitute in that a value. So in this section, I did want us to get a lot of practice with writing the definition of the derivative using both the regular and the alternative definitions at different a values.